Hello friends, let us resume our discussion on the second law of thermodynamics. So if you look back, we wanted to understand the second law of thermodynamics. For that reason, we introduced the concept of heat engine. We translated it to the Carnot cycle. And the Carnot cycle helped us understand or relate the theoretical understanding of certain concept to that of the physical world. And this relation helped us arrive at few statements and few laws, and these laws, they were equivalent, and this we categorized as the second law of thermodynamics. The way we arrived at second law of thermodynamics was just by relating the theoretical derivation in the framework of thermodynamics that largely involved operation of an heat engine and relating it to the physical world. Now, even though this seemed like we are taking a detour of what we are essentially interested in, we are interested in materials, we are interested in phase changes, the involvement of Carnot cycle might appear to be some sort of a detour. It helped us understand or reach one of the critical concepts of thermodynamics, namely the entropy. So it is through the Carnot cycle, if you could recollect, we ended up defining what an entropy is. So what entropy helped us do was, the entropy as a thermodynamic variable, it helped us quantify the changes that occur in a material. So supposing when you consider the translation of the operation of a Carnot cycle into a cyclic process, and this cyclic process comprises of two events, one occurring at one temperature and the other occurring at another temperature. So if you consider or translate the working of a Carnot cycle at two different temperatures, or working of an heat engine and a reverse heat engine at two different temperatures, the way we defined the changes that occurs to the system because of the heat transfer and the work done was a unique description. For instance, we considered, just for our recollection, we considered a system at A, and a specific amount of heat Q1 was allowed to pass through the system, was allowed to enter into the system, and this changed the state of the system from A to B. Now this occurred at temperature T1. Now once the work has been done, and once the system or this work has been rather induced by the transfer of heat of amount Q1, and once the system has reached state B, which is now an equilibrium state, we removed heat Q2, and this, the reversal of the change in the state of the system from B to A occurred at a different temperature, that is T2. Now when we wanted to quantify the change that has occurred into the system, the change that has occurred when you pass through amount of heat Q1 into the system, which is at state A, that allowed the system to pass to B, we quantified it as Q1 by T1. So one way of expressing the change that is induced by the transfer of heat to the system at a specific temperature, we introduced that, or we quantified it as Q1 by T1. And the reversal of the change as the system moves from B to A, once the heat is removed, we quantified it as minus Q2 by T2. Considering that this is a cyclic process, these two, and considering that the system that started at point A needs to get back to point A in order to complete the cycle, then the changes that occurred as the system moved from A to B needs to be reversed so that the system gets back to A. So since the change is quantified by Q1 by T1, and this change needs to be reversed in order to ensure that the system which is at B should come back to A, then there needs to be an equivalency. Therefore Q1 by T1 should be equal to Q2 by T2. Now, even though this is not how we arrived at this particular relation, this is what the meaning of this relation is. This particular relation, we spent quite some time in order to arrive at this particular relation. We considered the operation of an heat engine, we considered the overall operation of the Carnot cycle, we quantified the work done by the system, we considered both non-adiabatic isothermal changes and adiabatic non-isothermal changes. All these things we considered, all the changes, all the different events that constitute a Carnot cycle, we considered that. We considered the work done during the passage of heat, during the removal of heat, all these things we quantified, and then after doing several steps, after performing several numerical operations, we finally arrived at this relation. So there was an entire lecture dedicated to arrive at this relation. However, Once you have arrived at this relation, it is possible for us to interpret this relation in a different manner, and that is what we have done so far. So what essentially the left hand side and the right hand side means is that left hand side and the right hand side of this equation, it just quantifies the changes that occur in a system at a specific temperature when you allow the specific amount of heat to pass through. So therefore, on the right hand side of the equation, you have the work done by the system when Q1 amount of heat is allowed to pass through the system. The system is at A, you allow Q1 amount of heat to enter into the system at temperature T1. The system moves from state A to state B. Now, in order to ensure that the system gets back to state A, in order to ensure that there is a complete reversal of the changes, whatever that have occurred, that has led to the system to move from A to B, to achieve that complete reversal of the changes, you are removing a specific amount of heat, Q2, and for the system that is now at temperature T2. So this specific amount of heat that you remove ensures that the complete reversal is achieved. So therefore, you are reversing the changes that you have introduced at temperature T1 by passing the heat Q1, and therefore you end up with this relation. So this relation, when you consider what it means in a real or when you consider what it means in the scheme of things that involves changes and the reversal of changes, what you essentially have is, in case of a reversible cycle, in case of a reversible change, what you end up doing is you end up reversing whatever changes that have occurred. So in case of a reversible process, in case of a reversible reaction, what you are essentially doing is you are attempting to reverse whatever change that has been introduced by the heat transfer into the system. And in order to do that, you are removing a specific amount of heat. Had this been an isothermal change, an isothermal reversible process, imagine, had this been an isothermal reversible process, T1 will be equal to T2, so that means Q1 will be equal to minus Q2. So substituting T1 will be equal to T2, when you substitute this here, then the denominator gets cancelled out and you will end up with this relation here, that is Q1 will be equal to Q2. So what essentially this means is that you are essentially introducing a Q1 amount of heat and the system reaches state B, and you are removing the same amount of heat and the system reaches back to state A. So essentially what then you are doing is, whatever changes that has been introduced by the induction or by the absorption of heat by the system is being reversed by removing the same amount of heat. So that is what this expression here means. So this is rather straightforward for us to understand when we consider the isothermal reaction. So even though the bottom line here is, even though we arrived at this expression in a quite rather not in a straightforward manner, but understanding this expression is rather straightforward, what essentially we are doing is, whatever changes is made to the system by the passage of heat at a specific temperature, we are reversing that change by removing certain amount of heat depending on the temperature. So the amount of heat you remove in order to reverse the changes depends on the temperature. When it is an isothermal process, you introduce a heat, that is a change in the state of system, you remove the same amount of heat, the system reverses back to its original state. Now this expression here that ensures, or that rather explicates, or that rather reveals or unravels the change in the state of the system during a reversible process can be expressed in a different way, meaning it can be expressed in this way it is. So essentially this again only when it is here, this negative sign has a significance, but here since we are equating, this should be a positive sign. Only when this is on the other side, wherein we are collectively considering both heat input and the heat output, there will be a negative sign because this is heat removed, and once you bring it on the other side, this becomes positive. So I hope we're able to correct that. Now once we have arrived at this expression, it is possible for us to express the overall reversible process in this manner, that is T1, Q1, the change that is occurred by the passing in of the heat or the absorption of heat by the system, and the change that is occurred by the removal of heat at specific temperatures, that is T1 and T2. When you consider the overall change is 0, thereby characterizing a reversible process. And this is what we discussed here, and this is how we write the overall expression. Now when you consider a reversible process that involves numerous steps, all these steps operate in such a way that if a change is brought about by one step, it will be reversed by another step. Then that step need not be immediate, it can be after a while, but nevertheless, whatever steps that have been introduced by a given heat flow, it will be eventually reversed. So it is like you could construct, for instance, you could construct a system like this, and ultimately whatever change is brought about by this particular event here, it is reversed by this. Whatever change is brought about by this event here, it is reversed by this, and ultimately you end up at your original state. So irrespective of the number of steps that is involved in the reversible process, the overall change when you consider to the system will be equal to that of the the system will not experience any change, and that is what characterizes the reversible process, and this is the criteria that dictates this reversible process. And therefore this reversible process criteria, even though here it just involves one step and just a forward step and a reverse step, it is possible for us to have any number of steps. So therefore the generalized expression looks something like this. So here it is important for us to note that the summation is considered here instead of, even though if you bring this negative sign out, it should be minus. The reason summation is considered here because the negative sign comes from the convention. So therefore, whenever you are expressing the criteria for the reversible reaction based on this relation here, we should ensure that the appropriate convention is used for this generalized expression. Now, in the previous lecture, or in the lecture before that, we expressed this change, or we described this expression here, that is the heat that is introduced into the system at a specific temperature and the changes that is brought by it as the change in the entropy. So essentially there is a change in the entropy that is introduced, or the change that is introduced to the system by the passages or the removal of it at a specific temperature. We refer to it as the change in the entropy, and essentially what we then mean is if we express the change in the state of the system in terms of a change in the entropy, then what essentially we mean by that is when there is a reversible process, then the change in the entropy for this reversible process is 0. So what we have essentially done in this expression here is whatever change that is occurring during a process or during particularly a reversible process is 0. So this is what is rather a criteria that dictates or a characteristic feature of the reversible reaction. Now we are able to introduce a thermodynamic variable in order to account for this change that involves the heat transfer and also the temperature at which the heat transfer is occurring. So therefore we can write this expression using this new thermodynamic variable, that is the entropy. So when entropy, it rather describes the change that has occurred in the system, and particularly in the case of the reversible process, you have two different events, and according to these two different events, one forward event, another reverse event, and each of these events, they have their specific changes. And so this is the forward event and this is the reverse event. You have the specific changes. So this forward and this reverse, you have specific changes that are occurring during the forward and the reverse event, and correspondingly you have the specific, we can quantify the specific change in the entropy. However, when you consider the overall reversible process, we essentially end up having an expression something like this, wherein equal to 0. So this is the expression, which means when you consider the overall change in the entropy for a reversible process, it is 0. And when you make your steps that constitute your reversible process into a minuscule one, into a much smaller one, into a negligible one, then this change, this characterizing expression can be expressed in this, or can be written in this manner. So what essentially we have is similar to the internal energy, a thermodynamic variable that we introduced to describe the state of the system. We here introduce thermodynamic variable to describe the change in the state of the system. So if you could recollect, the reason we focused on, the reason we wanted to move away from the first law of thermodynamics is primarily because we are interested in dynamic system, not alone the static system, but we are interested in the dynamic system. Now therefore what we are then interested is in the thermodynamic variable that helps us understand the change in the state of the system, not just the state of the system, but change in the state of the system. So that thermodynamic variable is the entropy, and you have a specific expression for this entropy. Now this variable that is used to describe the change in the state of the system, when you consider a reversible process, the overall change in this variable is 0. that is a characterizing feature of the reversible process. So for second law of thermodynamics, you have introduced a new variable, that is entropy, and when you consider the reversible process, then the overall change in this entropy is 0. Now, in our previous lecture, based on this expression, we were able to arrive at an expression for or criteria for the non-reversible process. So far, we have been considering the reversible process. However, in nature, we have more than the reversible process, we have considerable amount of irreversible process that are occurring. So if you could recollect during while introducing the second law of thermodynamics, one description that we gave for the irreversible process is when the system moves from an unstable state to a stable state. So essentially what is happening here, even here, is when you have a system at state A and you allow the system to gain some heat, when you pass some heat into the system, what then happens is the stability of the system at state A is disturbed. So therefore the system moves to a new stable position. This movement of the system from the unstable state to a stable state is what we refer to as the irreversible reaction. So whenever you talk about, say, solidification, whenever you talk about, say, freezing, whenever you talk about a phase transformation, what essentially we are observing is an irreversible process. Of course, this change can be reversed. So whatever you see happening in your freezer, like if you place some water in it, the water freezes, that event specifically is an irreversible event. Of course, when you take that water out and keep it in the room temperature, it will eventually get back to the liquid status and it will eventually get back to its water state. However, when you place it in the freezer, for that instance, for that condition, for that removal of heat, what essentially you observe is an irreversible change from the water to solid ice. So what essentially happens is at that particular instance, once you place the water in the ice, that particular phase change is rather irreversible. Now, what essentially we have considered is, we have considered the whole cycle. That is, you are placing the water in the ice, or rather in the freezer, it changes into ice. You are removing the ice, placing it at the room temperature, it gets back to water. You are doing this cycle, and when you consider this whole cycle, then the overall change in the water is rather, for a given cycle, the overall change in the water is 0. So that is what we refer to as a reversible cycle, a reversible process, and for that, the overall change in the entropy is 0. Now, we want to break this down into irreversible processes, meaning when you want to consider just when you place the water into the freezer, and we want to consider this new change in the stability, this new change in the equilibrium, and the criteria that allows for the water to change into solid. And in order to do that, if you could recollect, we broke down this expression. We consider this particular expression that characterized the reversible process. We just consider two steps of it. So Q1, T1, and we consider minus of Q2 and T2. Originally, for a reversible process, this 2 should be equal to 0. That would be reversible. So this is the input heat and this is the output heat. So input heat is user defined, meaning you can input any form, any different variables, or any amount of heat you can feed in. For a given temperature, you can feed in any amount of heat. So this is rather, if you could consider for this expression here, if you could relate it to this expression here, this is rather an independent variable. You could treat this reasonably as an independent variable. However, this then would be a dependent variable. So what we can, in order to then introduce an irreversibility, what we need to do is we need to reduce this value. So only when you reduce this value, this balance is disturbed, and therefore in order to reduce this value, you add Q bar, you introduce or you include an heat, or if you feed in a heat of Q bar at temperature T2. So when you do that, what essentially happens is this then disrupts this balance and therefore brings about a certain degree of irreversibility. So you feed in Q1, you remove Q2, this brings back your system to its original state. Now in addition, while removing Q2, you also feed in some Q bar, then the system will not reach its original state, but it will reach some state here, say A bar. So therefore you have introduced certain degree of irreversibility. So this is what we are interested in, and this here, this term that brings about the irreversibility, it has an expression that is similar to that of the entropy which we have considered. So essentially what we have is, we have introduced an irreversible entropy, which in this simple example is the ratio of Q bar and T2. So what if you express it in a generalized manner, it is similar, the description is similar, but here we are introducing an irreversible change. So this irreversible change, it disturbs this balance. So the greater this ratio is, the greater the irreversible entropy is, the greater is the heat that you feed in during the reversible process, the greater will be the irreversible change. So it can be here, it can be here. So the irreversibility can be here 1, it can be here 2, or it can be here 3. So this all depends on how much of irreversibility that you are introducing by refeeding the Q bar amount of heat. When you increase the amount of Q bar heat, we are refeeding here. So this is plus, so meaning we are refeeding it. So when you are refeeding this Q bar amount of heat, the more you feed it back to the cyclic process, the more irreversibility you get. So what essentially we are doing is, we are increasing the irreversibility by increasing this particular ratio here. By increasing this particular ratio here, by increasing this term here, the more you increase this term, the more you disturb this balance equation, and the more you disturb this balance equation, it means the more you are increasing this means the more you are increasing the irreversible entropy. So the entropy change, that for the irreversible or the irreversible entropy change, you are increasing. So it means for an irreversible process, the change in the irreversible entropy is greater than 0. It is always increasing. So you have now two different conditions. One, for a reversible process, you have the change in the entropy is rather 0. So the change in the entropy for a reversible process is 0, and when you consider the change in the entropy for an irreversible process, it is positive, and it keeps on increasing as the degree of irreversibility increases. So the second law of thermodynamics, again the point where we started from, the second law of thermodynamics, the statements we had initially was based on the operation of the Carnot cycle. So this operation of the Carnot cycle, relating it to the physical world, we were able to arrive at two different forms of and two different statements for the second law of thermodynamics. Now from that, taking that as our foundation, we built or we arrived at a specific variable, a specific thermodynamic variable called entropy, and now our discussions were largely based on this entropy. Now based on this entropy, it is possible for us to describe the second law of thermodynamics. So one statement for the second law of thermodynamics is, whenever you have a reversible reaction, the overall change in the entropy is 0. So this is first law, or the first statement of the second law of thermodynamics. So whenever you have a reversible process, the overall change in the entropy is 0. On the other hand, whenever you have a reversible process, the change in the entropy, so whenever you have an irreversible process, whenever you have a system moving from an unstable state to a stable state, then in that case what you essentially have is an increase in the entropy. The entropy change, the entropy that allows for the system to move from an unstable state to a stable state, the entropy that allows for the irreversible process is positive, and as the system moves from an unstable state to a stable state, the entropy keeps on increasing. So let me repeat. You have two different statements. One is straightforward entropy. If you consider, if you define, or if you assume or reasonably describe entropy as a quantification of a change that occurs in the system, then for a reversible process there is no change, ultimate change that is occurring to the system. So therefore for a reversible process, the overall change in the entropy is 0. Now for the irreversible process, the degree of the entropy can be referred to as, to going back to our canonical description, the entropy can be described as the degree of the irreversible change. So therefore, as a system moves from one unstable state to a stable state, then the degree of irreversibility needs to be increasing. Now even in this description, we saw that the change, or rather the irreversible entropy, needs to be positive for an irreversible reaction to occur. If it is 0, essentially we go back to our reversible process. So in order to have an irreversible process, the entropy change should be positive, and only when the entropy change increases, then the overall entropy or overall irreversible change occurs. So only when there is an increase in the irreversible entropy, there will be a progress in the irreversible reaction. So this is rather a pivotal statement of the second law of thermodynamics. So if your system reaches a state wherein it is not possible for the system to change any further without decreasing the irreversible entropy, then the system will not move any further. The system will move further. The system will exhibit an irreversible change if and only if there is an increase in the entropy. So this statement is universally valid. It is not confined to rather a material system. It is not confined to atoms. It is not confined to rather operation of a heat engine. It is not confined to a specific system. It is universal. So this second law of thermodynamics, that is why the emphasis is largely posed on, whenever we talk about thermodynamics, the emphasis is largely posed on the second law of thermodynamics, because whenever you talk about an irreversible change, there should be an increase in the entropy. There should be a corresponding increase in the entropy. An irreversible change will not occur with a decrease in the entropy or the entropy staying constant. Now, another statement, the third statement that could be included to the second law of thermodynamics based on the entropy is, whenever you have a system at a stable state, then the overall change in the entropy then again is zero. So the overall change in the entropy for a system at a stable state is zero. Now, one way of understanding this is again considering a system that absorbs heat, say Q1, at temperature T. It's an isothermal system, and essentially you remove the specific amount of that heat, the same amount of heat, and what essentially you are doing is you are allowing a heat to pass through the system. You are allowing the system to absorb Q1 amount of heat at temperature T1, and you are removing Q2 amount of heat from the system, but you are not allowing the system to change its state. So essentially then what you are doing is, you are whenever you want to quantify, or in this case when you want to quantify the change that is occurring to the system, essentially it would be like Q1 by T and minus Q2 by T, and you consider the overall change in the system, then it will be this. And if you could recollect, just moments before we saw that Q1 and Q2 will be equal for an isothermal cyclic or isothermal reversible process. So essentially what you are doing is, you are feeding in some amount of heat to a specific system, and you are removing the same amount of heat from that specific system. So essentially then the system does not change its state, it remains stable. So it just remains ideal, so it remains static. Even though you are feeding in heat and you are removing a specific amount of heat, and you are, in this case you are removing the same amount of heat, what essentially you are doing is, you are not bringing about any change to the system. You are just allowing the heat, this amount of heat, to pass through the system, and the same amount of heat that enters in is the same amount of heat that passes through the system and that is removed out. So therefore the system in itself experiences no change. Now when the system in itself experiences no change, then you can just sum these two up and you will arrive at this expression that this is zero. So essentially what happens is, and these are nothing but the difference of this term here, it quantifies one change entropy and this other entropy. So ultimately the system does not experience any change. So ultimately, similar to the reversible cycle, when the system is in its stable condition, the overall change in the entropy is again zero. So what we have here is a system that does not exhibit any change in its state. However, even though there is a heat that is introduced or included in the system and the heat that is removed in the system, and since there is no change that is occurring to the system, then the overall change, that is Q1 by T, and here since the heat is removed, Q2 by T, the overall change will be equal to zero, and here this individual terms are nothing but the entropy. So overall the change in the entropy, that is D, is zero. So this is one other criteria that dictates the stability of a system, a given stability of the system. So whenever you say a system is stable, or whenever you say that a system is static, it does not exhibit any change, then there is no corresponding change in the entropy of the system. So the second law of thermodynamics, it gives us three different statements when you discuss or when you describe it based on the entropy. So it considers reversible process, it considers irreversible process, and also it considers a system that is in static condition. So it considers both dynamic condition and it considers also the static condition. In dynamic condition, it talks about reversibility and irreversibility. In dynamic condition, or in static condition, it talks about a system that is stable. Now, just to pull all these things together, essentially what you have is whenever your system exhibits a reversible process, the overall change in the entropy is 0. One statement of the second law of thermodynamics. And whenever the system is in its stable condition, is in a static state, then the system, there will not be any specific change associated with the system, therefore the change in the entropy is again 0. The most critical statement of the second law of thermodynamics is whenever you see a system exhibiting an irreversible change, then during the process of the change, the entropy should increase. The entropy is the governing. If you give, you can also, it is possible for us to give this perspective rather, that the irreversible change is possible only when there is an increase in the entropy. You need to have a positive change in the entropy in order to introduce a irreversible process, and this positive entropy needs to be increasing when you need to keep on maintaining the dynamic nature of the system. Now, with this idea, if you plot, see for instance, a system is at A and it needs to move or it needs to change, or it stays from A to B, and you are calculating the change in the irreversible entropy, you are calculating the change in the entropy as the system moves from A to B, then you would find that the entropy keeps on increasing. So of course the way it keeps on increasing depends on several factors, but however the entropy keeps on increasing. So this is how the schematically, again this is a schematic representation, it is just qualitative, just to understand how entropy influences the change, irreversible change in the state of the system. So what essentially you have is, you have an unstable system A or state A, and you have a stable state B as the system moves from state A to B irreversibly. So it is unstable, it is stable. So let me highlight the unstable in red. So this is unstable and this is stable. So again, so as the system moves from A to B, what you essentially observe is the entropy of the system keeps on increasing, and as it reaches B, it is in its maximum, and there can be no further increase in the entropy. So beyond this point, there can be no further increase in the entropy, and only then the irreversible process stops. So the entropy change, it governs both the dynamic and the stable static state of the system. So the irreversible process, the dynamic state, is governed by the increase in entropy, and as long as the entropy keeps on increasing, as long as the entropy is positive, as long as the entropy is increasing, the system progresses towards its stable state. And once the system has reached its stable state, there will be no longer any change in the entropy. So that is the third statement here. So once you reach the stable state, system reaches the stable state B, there will be no longer any change in the entropy. So the dynamic condition is described by the statement here, that is indicated in red. The static condition, it is highlighted by the statement here. So once the system reaches a state wherein there is no possible way of increasing the entropy, then the system has reached a stable state. There will no longer be any change in the entropy. So when you consider a change in the state of the system, and when you consider how the entropy increases, you will notice that the stability point indicates the stable point indicates the maximum change in the entropy. So essentially, the change in the entropy would look something like this. If you consider, so the change in the entropy as system moves from B to A, or A to B rather, it looks something like this. So here, again, this is schematic. This is not anything specific, just to understand, gain a conceptual understanding of the change in the entropy. We are doing this. So there is a change in the entropy that keeps on increasing, and once it has reached its maximum, we have arrived at a stable state. So it starts from A, and it moves towards another stable state B, and this stable state B, once it has reached this stable state B, there is no further increase in the entropy. There is no further change in the entropy. So instead of ds here, it should be here. So the change in the, again here, it should be the entropy alone. So again, this increase in the entropy, it stops at some point, and after which there is no change in the entropy. Here the slope is 0. So this axis, it indicates entropy. And when the system moves from an unstable state to a stable state, there is an increase in entropy, and after a while there is not much change. And the maximum of this point, it indicates the first moment it reaches this particular point here, it indicates that the system has reached its new stable state, and this new stable state is characterized by the maximum of the entropy. So whenever you see a plot, be it for a phase transformation, be it for any process, whenever you see a plot that rather quantifies the change in the entropy, the point where the maximum entropy is reached, that is what dictates the or the duration or the instance when the system has reached the stable state. So in this case, the system has reached the stable state at this point here, and after this there is no change in the entropy, meaning here it is the system is in equilibrium, and here there is an irreversible process. So this overall the plot that you have can be distinguished into two: one wherein there is a dynamic change in the system, the dynamic irreversible change in the system that is characterized by increase in entropy, and at the peak, once the maximum entropy is reached, then there is no further change in the entropy, so therefore there is an equilibrium state in the system. Now this again was a universal criteria, so this criteria can be used to describe any change in the state of the system. So whenever you see whenever you are able to estimate the entropy, then based on plotting the entropy you will be able to estimate, or you will be able to say at which point the system has reached an equilibrium. Now in addition to that, one other role or one other usefulness of the entropy, one other aspect wherein the entropy plays a critical role is for us when we want to understand, say, a given composition of a system. Supposing you have a system which combines, for instance, ice and water. So you have a system which has combination of both ice and water. So you have a system, let us imagine a water bottle that comprises of both ice and water, and this ice and water, the volume fraction of the ice and the volume fraction of the amount of ice that is present and the amount of water that is present. So volume fraction of ice and the volume fraction of water, it remains the same, it is not changing. So what you have now is an equilibrium condition, a stable condition that comprises of two phases. You have ice that is in solid phase, you have water that is in liquid phase, and these two phases, they coexist at a given within a given system. At a given temperature, a combination of temperature and pressure, you have a system that comprises of two phases that coexist with each other, that does not intermingle, that does not exhibit any phase transformation, one does not change into another. So you have a definite volume fraction of ice and a definite volume fraction of water. This does not change. So you have a specific volume fraction of ice and a specific volume fraction of water. So there is no much change in it. So what does that mean is we have established a system that is in equilibrium or that is stable, and what you essentially so what we mean by stability is there is not much change or increase in the volume fraction of increase and decrease in the volume fraction of ice. So you don't exhibit, there is not much change in the phase fraction, or there is not much change in the volume fraction of ice, or not much change in the volume fraction of water. So you have a system where two phases coexist, ice and water, they coexist. So when you consider the volume fraction of ice and when you consider the volume fraction of water, so volume fraction is the volume of ice, the ratio of the volume of ice and the overall volume of the system, and the volume fraction of water is the volume of water and the overall volume of the system. Now since these are two different phases, we refer to them as the phase fractions. So the phase fraction, it does not change. The volume fraction of ice and water, it remains constant, so that means there is no much dynamic change that is occurring. Now you have this system at a specific temperature T. Now we want to find out what would be the volume fraction of the ice. What is this volume fraction of ice and what is the volume fraction of water? You want to be specific about what is the different volume fraction of ice and the water that is present. Now it is possible for you to calculate, imagine a condition, it is possible for you to calculate the entropy change associated with the different combination of ice and water at that temperature T. So you are working on a temperature T, you are arrived at a system that comprises of two phases, ice and water, in a definite proportion. Now you want to find out what is the volume of ice that I have and what is the volume of water that I have. In order to do that, what you do is you calculate. So one way that is possible for us to identify, to calculate the volume fraction of ice and the volume fraction of water is to calculate the entropy associated with the different combinations of water and ice for this temperature T. So at one end of this plot you have what completely a system that comprises completely of water, and the other end you have a system that is completely comprising of ice. So now you are able to calculate the entropy of the system that completely comprises of water and the entropy of the system that completely comprises of ice, and you also have different mixtures in between. So this would be, say for instance, here it is 100% water and here it is 100% ice. So here it would be 90% water and 10% ice, 80% water, 20% ice, and here it would be 10% water, 90% ice. So here 100% water, here 100% ice rather, and in between you have mixtures of ice and waters at a different proportion. So as you move along the x-axis, you would have systems with mixtures of ice and waters at a different proportion. Now for each of this combination, so for initially you calculate the entropy of pure ice, or rather pure water, say SW, and you calculate the entropy of pure ice, say SI, for the specific temperature T. Then you calculate for each and every combination, 90% water, 10% ice, you find it to be somewhere here, and 80% water, 20% ice rather, you find it to be somewhere here, and so on and so forth. You calculate the entropy for different combination at temperature T, and you find out the entropy changes with the volume fraction of the ice and water in this manner. So you calculate you have a system that comprises of two phases, water in the form of ice and liquid. So you have a system that comprises of ice and water, two different phases. Now they are in their stable state, they are not exhibiting any change. Now you want to know what is the volume fraction of ice that is present and what is the volume of the water that is present in the system. In order to do that, you calculate the entropy. Theoretically, you calculate the entropy of pure water and ice and all the different combinations of ice and water within the system. And once you calculate it, you plot it in this format here, wherein you have at the one end pure water and the other end pure ice and all the combinations in between, and now you calculate all the different values of the entropy for the different combination, and you get a plot something like this. Now since this change from water to ice is rather irreversible, whenever you consider a change from the water to ice, this change is rather irreversible. This can be only reversed when you are able to change the amount of heat or that is being removed. So essentially each of these states indicate a stable state. So essentially what we have is, we have now calculated the entropy associated with this different combination at the temperature T. Now we saw in our previous discussion that whenever there is a possibility for a system to increase its entropy, then essentially there would be a change in the state of the system. So in that case, so let me repeat, essentially what you have is, whenever you have the possibility for a system to increase its entropy, then the system will attempt to move to the state wherein the entropy is increased. So what essentially we have from the second law of thermodynamics is, for an irreversible process, it is characterized by it. So irreversible process means increase in entropy. So when a system wants to achieve a stable state, it has to reach its maximum entropy. So if we assume the system is in this state here, then it has the possibility of increasing in entropy and reaching this point here. And if a system is in this state here, it has the possibility of increasing entropy and reaching a state here. When the system is in this state here, there is no possibility for the system to further increase its entropy. The system has now reached its maximum entropy state. So this means that the system will not exhibit any change in the entropy. So there is no possible way for the system to decrease in its entropy. So only possible way for the system to change its entropy is to state zero or to increase. So that is what the second law of thermodynamics states. So there are only two possibilities. Either the system or the entropy of a given system can remain unchanged or it can increase. So when it remains unchanged, then there are two possibilities. One, it is exhibiting a reversible cycle, or it is at its stable state. and when it is increasing, then it means that it is moving towards a new stable state. Now that understanding, when you pose here, for all these different volume fractions, for all these combinations of water and ice, there is a possibility of the system, for all these combination of water and ice, there is a possibility of the system increasing its entropy. However, for this point here, let's say O, for this point here O, there is no possibility of the system increasing its entropy. So the only possibility you have is system maintaining its entropy without exhibiting any change. So that means, according to the second law of thermodynamics, the system has reached its equilibrium state. So then what we can essentially do is drop a straight line and find out what is the corresponding volume fraction. So here it could be close to say 75, or rather 65 and 35. So 65% water and 35% ice. So then for a system at temperature T, which we have considered, which comprises of two phases, water and ice, the volume fraction of water is 0.65 or 65%, the volume of ice would be 35%. Now the way we were able to estimate it is by considering the entropy of the different combination for a given temperature and relating it to the second law of thermodynamics. So the second law of thermodynamics states that if you want to consider a generalized expression for it, the entropy can either increase or it can stay the same. For all the other volume fractions, for all the different volume fractions of water and ice, there is a possibility of increasing the entropy. So those are not stable states. The only place wherein the volume, or the only state wherein the change in the entropy is not possible is at O. So therefore the point O is the stable configuration, is the stable volume fraction. So essentially, whenever you have a system at its stable state, it is possible for us to estimate the features of such a system by considering its entropy. So the second law of thermodynamics, it gives us different statements. It helps us describe a static system, it helps us describe dynamic system, be it reversible or irreversible. In addition to that, what the second law of thermodynamics does is it helps us identify or describe the features of a stable two-phase system. So it helps us describe the feature of a given stable system. So this is here in this example, we have seen that it is possible for us to identify the stable state of a system, the static state of a system using our understanding of the entropy. Now the same again can also be, the same understanding can also be gained, or the same results can also be arrived at from our second law of thermodynamics, which we have considered, that is here, meaning a system is at a stable state. Whenever you see a change in the state of the system is at a stable state when the entropy is at its maximum. So this is one way of describing the second law of thermodynamics. So whenever you see an irreversible change in the state of the system and the system reaching its stable position, and it means that when the system reaches a stable position, the entropy of that particular system. So you consider a change in the state of the system from unstable to stable, and when the system reaches its stable position, the entropy of the system will be maximum. The same understanding can be adopted here, and since the maximum point is here, you will be able to then identify or describe the stable state of the system. So what essentially we have done is we have expressed the second law of thermodynamics purely based on entropy, and this gives us a way to identify a stable system. This helps us describe a stable system and what constitutes a stable system. So essentially what we have done is we have considered different combinations for a given temperature. We have considered combinations of different phases, different volume fractions of two different phases, and from that we were able to identify which combination is stable. So essentially this can be extrapolated to any number of materials. So whenever you see a system that comprises of different phases, now the stable volume fraction of these phases can then be estimated by considering the overall entropy of the system. So whenever you see a system that has its maximum entropy, then that system is stable. So whenever there is a possibility for the system to increase its entropy, then there is a possibility for an irreversible change. The system has not yet reached its stable condition. So with this, I would like to wind this lecture up. So whatever we have seen is most critical here. The entropy is now helps now the entropy is a way for us to describe the stability of the system and also describe the feature of or identify the specific feature of that stability. So we'll see in ourselves in the next lecture wherein we will build on this. Goodbye.